All right, here we go. Linear motion. Linear motion will be the easiest chapter with the most equations. And we'll get into this in class, but the video actually gives you a good idea to start linear motion and start thinking about things in certain concepts. The idea behind linear motion is between point A and point B. That's the biggest goal, to find out where everything's at, how fast it got there, what was the velocity, what's the acceleration. There's a lot of different equations to use depending on the information they give you. So, as I've said before, one of the hardest parts is getting started, and the last part, which is the hard part, second hard part, so to speak, is explaining your results. If you can't do anything else, if you can set up the equation, figure out what you're supposed to do, and then explain the process, even without solving the math, you will do well in the AP exam. I can't stress enough explaining and understanding. That's what the AP examples are going to be. I've seen scores on the AP exams that are really high and the math is really wrong. If you've heard it before, I'll tell people all the time, I was like, it's amazing when people get into physics and AP physics, they'll do this complex equation, be able to explain it perfectly, and make a stupid, that's the only way you can drive a stupid mistake. Like, do all the math, all the equations, you've ran down the entire sheet of paper, and they've rounded 12.48 to 5.8. Like that doesn't round. Like, every year it happens at least once or twice on a test, on an exam, and the explanation's perfect. But that last part of checking your answer, it's just like, what happened? Anyway, so here we go. Let's talk about linear motion. So the idea is here. Yeah, my mouse will work. There it goes. Just like in a lab you did, is understanding equations, finding the slope, finding a point at a time what the slope of the line is. This is a very simple example where you sit there and it's linear, it's going up. You can do rise over run. Again, rise over run. I don't know how many times you've hopefully heard that in your math class. Rise over run. Rise is the y, x is the run. In this case, they used, for their example, delta y over delta x. They said the increase in y was it went up 4. You can pick any points on a linear graph and go, okay, I'm just going to pick 0 and 1. 0 being the line, and where it crosses on the x-axis is the 1. That's what the point I'm going to use. That's where I'm going to start. Go, oh look, I'm going to go over on the x-axis to 3 and up to 4. Done. You've just figured out I went on the y-axis, I went from 0. I went 0 up to 4. That's my change in y. On the x-axis, I went from 1 to 3. So I went over 2. And then the slope is positive 2. Positive 2 shouldn't automatically clue your brain into it's going up. So hopefully that is very simple. Hopefully you can do the lab. Hopefully it was there very quick. You've got it. You're doing that. And there's our cool little graphics. Oh yeah, I take for granted you guys know Greek alphabet. Delta is a little triangle. Please say delta, don't say triangle. So example, the delta y is a change in y. Final minus initial. Regardless of what you're doing, final minus initial is actually going to help you in a lot. If it's position, if it's velocity, change in acceleration, the final minus what the initial was, okay? All right, something a little harder. Rise over run. We have to pick a point. So we sit there and say, okay, same slope as you're choosing point on the graph, cool. The slope has a positive 2. This is a nonlinear function. Could be a quadratic, it could be a polynomial, could be an exponential. So, actually this graph probably couldn't be an exponential, but that's another argument. So, at a given point, we sit there and say, okay, cool, that is the slope of the line at that point. Depending on the point we're looking at, it becomes easier or harder. So you'll hear the phrase tangent line is the line or the slope of the line at that point. Obviously, as you go further to the right, it's going to change a little bit more, but that'll be fine. So, all right. Simple object movement. If it goes from here to there in a straight line, it's a linear motion. Non-linear. Linear? Non-linear. Those are your two choices. Don't make it hard. So displacement is from x to y, or x to x. X initial, xi, to xf, x final. The example, they use x1 to x2. So your final, xf minus xi, initial, or as the screen says, the change in x is x2, your final position, minus your initial position. Easy, right? What if the path is not a straight line? I don't care. If I'm looking for distance from the start, the change in x is just that distance. If I'm looking for the distance a person traveled, that's the line, the squiggly line all over the place. Most of the time, you're concerned with they started where, they ended where. What's the distance between them? So, and there it is in word format. One of the things I will tell you that will get most people is that bottom third bullet. Distance has no sign, only has the magnitude. Displacement, however, which is what we want to use, the top half, has a magnitude, has a direction. So, can be negative or positive. In fact, the negative or positive actually tell you information. Okay? So, they use this example. If you walk, so your prize is 2 kilograms of gold at the end of a 3.2 kilometer walk from here. Yes? That's one option. The second option is your prize of 2 kilograms is exactly 3.2 kilometers east from here. The problem with the first example is you could walk all over you could walk through Nova Scotia and come back. Well, not really, because there's a big ocean in the way, but okay. But you end 3.2 kilometers from here. The bottom one is by far better because it assumes a straight line from the starting position 3.2 kilometers to the east. A little bit more useful and slightly different, but understand there's a huge difference in the two when you had to walk that distance. So, average speed, velocity, average speed, distance divided by time. In this case, more helpful, average velocity is displacement. You notice they're starting to use a lot of the subscripts. I'll highlight here. Let's see if it'll do it. Right here. They will use this over and over to indicate different options. Average velocity, and these subscripts are not set in stone. You can use whatever you like. I am not a fan of using words. You'll see other notations. You can even write V, AVR, or AVG in the X. So it's velocity in the X direction. So distance in the X divided by time, which is by far better than distance divided by time. Because this will give you a velocity. Cool, you'll go and you understand you're going 90 miles an hour in some direction. Displacement should give you a time and a position. So we'll talk more about that in a minute. So examples. So we've got a distance going over. Time goes in 3 seconds. We went 6 meters. Again, time versus distance in this case. Displacement was 6 meters. Change in time is 3 seconds. That would should give us a slope of the line. There it goes. Nope, didn't do it. This is another example. So, all right, so you get the point. I'm not going to waste your time with a lot of examples. We will probably do 1 or 2 of these. If you understand and do well in the lab, I think everyone should. Practice with the lab. It's actually quite good. And to be fair, it's one of the better ones I've ever seen about just getting you not drawing, not doing math, trying to figure out the slope of the line versus an equation. I will tell you, don't start with level, I think it's level 6, level 5, the highest level, because you need to go through the small ones just to clue your brain and get it fired back up and going on, okay, this is what it looks like. So you will have to do some labs where actually you'll have to do some charts where you sit there and say, okay, this is my position, looking down the right-hand side. and then this is my time. Okay, so we'll talk about those graphs, and we'll actually build quite a few of them in class. So, and there you go. You still get a velocity with a negative slope. Good to go. We'll do one or two of these in class. Instantaneous velocity, they love to do these. It's just a point. I'm going to say, okay, let's look at that point and find the slope of the line. So we just do a line. Oh, look, it's a tangent line right there. If my mouse was going straight, it would be better. But the idea is it's just what is the slope at that point? At this time, what's the slope of this line? At time here, what's the slope of the line? Should be easy to figure out. The charts, however, are kind of misleading. We'll talk about that as they start mixing in time, velocity, average acceleration, and time. And there we go. Add an instant, or that I like to use the word add as a point. Okay. Think you can do it? Rise over run. Cool. From point A to point B. Average. Again, 1 point, instantaneous. Between 2 points is your average. Huge difference. Instantaneous. I want to take an instantaneous snapshot of what you're doing. This one I would have to watch you over this time period. It's an average. Okay? I'm not going to go through that one. This actually is one of the better slides, I'll tell you right now. Velocity versus time, constant zero. Velocity up here. I will tell you right now, this will appear on the AP exam in some fashion. The problem that I have with the AP exam, especially the way it's given now, is these are not color coded. It's all black and white. So maybe next year they'll increase color and print them on color, but I doubt it. It's kind of annoying. But you can see the difference. Change in velocity, change in time. They'll even have some of this, say, acceleration over time. You have to be able to look. That's why I had to do the lab. Have to be able to do and actually do them. So I'll tell you a side note on the lab. I'm fully aware that someone could have done it and then taken a screenshot of it and passed it to a friend. At this point in time, most of you guys are seniors. There's a few juniors in here. If you want to cheat this class, you can. But the AP exam will be painful. So, all right, and we will practice a few of them. So we'll figure it out. Okay. If you have questions, let me know. And then lovely slopes, lines, average equations, and again, cool graphs. We're going to go talk about this slide in class as well. So, yeah, I forgot this slide was in there. Speeding up, slowing down. I hate the term speeding up, slowing down. I also dislike the term acceleration and deceleration. The only term there is acceleration. Is it a positive acceleration or a negative acceleration? Positive acceleration means I'm speeding up. You shouldn't say speeding up because it doesn't help you with a number notation. It's still a -2. Okay? So, because if it's an acceleration, my velocity example, my acceleration is -2, like it says on the screen, but my current velocity is -2, meaning I'm going backwards, then actually my speed is getting more, and the number is getting higher. For someone to see a negative acceleration and then think they're speeding up, they would have a problem. Unless you include the fact that the velocity was already negative. So I don't necessarily like it. If you want to use the term speeding up, slowing down, just understand I'll probably ask you, is it a positive acceleration or a negative acceleration? Just for that reason. So, oh, yay. And last notes. Area under the graph we've already been able to do. Not a fan of this because I'll tell you right now, it very rarely happens. So we will use the equation to find area under a graph, and you'll see why. It gives us a couple of equations we can use. They do it piecemeal and say, okay, can we get the area of that triangle and move forward? We'll go through some of these and calculate the area. You'll see why I'm not a fan of these, because there's some equations that just make sense otherwise. Equations you'll have to know. Yeah, it's not provided on the AP exam sheet. Hopefully you know that one. The other one you'll need is those bottom set. Again, slide 1, slide 2. You should already have them if you took notes. I love the ones on the right hand side. Hopefully you took those. If not, hopefully you knew them. When I write them in class, you'll see the red X, the red V, the red T. I will say XF and XI, VF and VI, TF, TI, just because to me, AP uses the note that X naught on that case is the initial, V naught is the initial velocity, T naught is the initial time. I just like the word initial, because if I'm already thinking it when I see the V naught, I'm thinking the word initial already. So we'll talk more specifics. Subscripts aren't a huge deal. If they help you, they help you. All right, we're gonna stop here because honestly, the rest of it we're going to go through in class. If everything makes sense on this, you should be pretty good. If you want to take a look at the bookwork and start there, you can. We're rolling right along. Again, as always, please, if you have questions, ask. We're going to do quite a few problems in class, and that'll be my focus. Use our time in class for equations and making not definitions the focus. You can look at definitions anytime. All right, good. Hopefully everything's going well. Again, let me know. I'll ask it in class. I'll ask it again. I'll probably put a form out saying, hey, what problems do you have? Please be honest, because unfortunately, example, one of my students in physics in the past, I could see when she was having a meltdown or about to lose it because she would reach in her bag and start using suckers and like chewing on them and gnawing on them and like shaking. If I can't see you other than Zoom, I might miss the fact that you're eating suckers, unless you're not on mute. Anyway, we'll deal with that later. Hopefully you're having a good day. Let me know if there's any issues. All right, talk to you later.